Recall that we had B r equals mu naught I over 4 pi integration d l prime cross r minus r prime over r minus r prime cubed in the previous lecture. I gave you a hint there in solving one of the problems, example 2, where I said that I can be written as k dx prime. In general, we can write current inflowing in some region as, suppose there is a thick wire. So, the current will be all over the place as a 3-dimensional wire. Then I can write I as some j ds, where ds is in the direction of j. J is defined as the current density, which is equal to current per unit area. And just to connect with what we did in the previous lecture, there I had surface current, which was equal to current per unit length. Just like we had charge density and surface charge density, here we have current density and current surface current density, which is current per unit length. We would like to write this as a vector quantity. So, we write I as equal to j dot ds integrated over the cross sectional area. So, for example, here I could have this cross sectional area like this, right. So, at this point S will be pointing this way, at one point it will be pointing this way, at one point it will be pointing this way, but the current is flowing in this direction. So, the dot product gives you that right answer, the projection of the area perpendicular to the current. So, then we define two vector quantities, right. So, I am going to call this j is current density per unit area in the direction of current. Let us put it that I like this, and then everything is consistent. So, what we now have is we have a B R formula mu naught I over 4 pi integration d l prime cross r minus r prime over r minus r prime cubed. We have a current density J r such that the current through a cross sectional area is J dot ds. Just to draw a parallel, right, just to draw a parallel with E field, we had E equals 1 over 4 pi epsilon 0 q r minus r prime over r minus r prime cubed, and we had charge density rho r such that integration rho r dV gave me the total charge q. And then here we had Gauss's law, which says del dot E is equal to rho or integration E dot ds. There should not be any circle over this. Surface integral is equal to charge enclosed divided by epsilon 0, and we had curl of E equal to 0. We would like to have something similar to this for magnetic field, because we saw once we had these differential equations, the curl and the divergence of E, calculating E became quite easy, right, through Helmholtz's theorem. And we also had in electric field something called the potential V r, the potential. So, again we like to have something similar for the electric for the magnetic field. So, without really showing how this comes about, let us write those equations. Divergence of B is going to be 0 always. So, this is a geometric constraint on B. Curl of B at a given point is going to be mu naught times j of r at that point. So, this relates the production of B through current density. Then corresponding to V r, we are going to have a vector potential A r. In this case, the potential is not scalar, but it is a vector potential because of this divergence. So, these are going to be my equations for the magnetic field, and the corresponding integral equation from this comes out to be curl of B dot ds is equal to mu naught j dot ds, and this gives you B dot dl by Stokes' theorem comes out to be mu naught times I enclosed by that loop. That is the corresponding equation, the integral equation for that differential equation. So, let us now write these purely for magnetic field. Earlier we just drew an analogy. So, I am going to have divergence of B is equal to 0, curl of B is equal to mu naught j r, and if there is this current J flowing, if I take a loop around it, no matter what kind, and I do B dot dl over this loop, this is going to be mu naught times I enclosed by this loop, and there is going to be a vector potential. So, we will take these one by one. Let us first do, how do we get del cross B equals mu naught j r from Biot-Savart law. I am doing this so that you start visualizing the currents and the fields and how do we manipulate this. So, let us see, if I have a loop, and let us make this a thick loop. So, let us do this. I have a loop in which a current is flowing, thick so that I can define a J. I have this thick loop in which current I is flowing. This is a section of the loop, and there is this current density J r in this. Let us say this is r prime. So, this current is flowing, and I have and this is steady. By Biot-Savart law, I have B at r is equal to mu naught I over 4 pi integration dl prime cross r minus r prime over r minus r prime cubed. Now, recall that problem that I solved in the previous lecture. So, recall the problem where a current was flowing in a strip. Like that problem, I can now write this I as J dot ds, Right now, let me write this as a scalar quantity j ds, and you will see the reason for that. So, let me write this as b r equals mu naught over 4 pi. I can write as j ds, and this will be at that prime position, right. So, j at r prime dl prime cross r minus r prime over r minus r prime cubed, where ds is perpendicular to the current direction, j is in the direction of the current. So, let us write this again. I am writing P r as equal to mu naught over 4 pi integration j at that r prime ds at r prime dl prime cross r minus r prime over r minus r prime cubed. Since dl prime is in the direction of the current and j is in the direction of current, I can write j r prime dl prime as equal to, put that vector sign over j r prime dl prime. So, if I look at the section where the current was flowing, this is the current direction, ds I am taking to be perpendicular to the current direction, and this vector is dl prime. So, if I look at this red section of the current carrying wire, this is the volume of this wire. So, I can write the above formula for B r as mu naught over 4 pi integration j r prime cross r minus r prime, because now cross product will be with that vector over r minus r prime cubed dv prime. So, we have now gotten a formula for the magnetic field in terms of current density. So, even if the current is distributed over some region, this formula is much more useful than the Biot-Savart formula in terms of the current. And you saw in that problem that we solved previously that how we use this. So, B at r is mu naught over 4 pi integration j r prime cross r minus r prime over r minus r prime cubed dv prime. This is similar to the electric field formula for a given charge density, which was 1 over 4 pi epsilon 0 integration rho r prime r minus r prime over r minus r prime cubed dv prime. The difference is, as I have been saying, this cross product, and that is what makes life little more involved. Now, from this it is easy to see that divergence of B is equal to 0 and curl of B is equal to mu naught J. To do the second part, you use the identity for curl of cross product of two vectors to calculate curl of B, and then again do the manipulations. Similarly, for the first part. So, I leave that for you. So, this proves proofs are now left for you to complete. I have given you a hint how to do it, and you have also seen the manipulation we did in the previous lecture. So, you should be able to do that. So, what we have now is divergence of B is equal to 0, curl of B is equal to mu naught J, and its integral form B dot dl is equal to mu naught I. This is known as Ampere's law. And this is the geometric constraint on B. What this tells you is that the derivatives of E cannot change arbitrarily. For example, I have dB dx plus dB y dy plus dB z dz is equal to 0. So, they cannot change arbitrarily. Similarly, for current free region, I am going to have curl of B is equal to 0, and this implies that dB x dy equals partial y partial x, partial B z, partial y equals partial B y partial z, and so on. So, these put constraint on B, and sometimes these can be used to find how electric field is varying in certain area of space if you know variation in some one direction. Let us do one problem using that. So, let us do a problem involving geometric constraints on B or its variation of B. This problem is taken from Jackson. This is Jackson, problem number 5.4. Says for cylindrical symmetry, if B s equal to 0, z is known, that is, this is Bz. Bz is known along the z axis, then for small enough distance near the axis, you can write Bz as a function of, the book uses rho, we have been using s, so I will use s. Z is equal to Bz s equal to 0, z minus s square by 4 d2 Bz over dz square at rho equals 0, and B in the s direction as a function of sz is given as minus s over 2, let me write it cleanly, minus s over 2 partial Bz over partial z at s equals 0 plus s cubed over 16, third derivative Bz over dz cube at s equals 0. This is a problem, and we are going to use the geometric constraints on B for this. So, let us do that problem now. So, in a way you may have been given this ring carrying charge, carrying current, and you know the field at height z. This we had already calculated. So, I could have B z at s equals 0 is equal to mu naught I over 2 r square over r square plus z square raised to 3 by 2. This we already knew for a radius of r. So, this could be that cylindrical symmetry situation, and what we are asking for is what is the field near this axis at a distance s at any z. For this, we can use the geometric constraints on B, and we are going to use cylindrical coordinates. Because that symmetry is there. In cylindrical coordinates, divergence of B is given as 1 over s d by ds of s bs plus d bz by dz, and plus there is a phi term which is 0 because there is no b phi. So, this is 0. So, what this tells you is that 1 over s d by ds of s bs is equal to minus d bz by dz at s equals 0. This gives you the first approximation, like a Taylor series, that Bs is as a function of s is going to be equal to, you can integrate the s part directly, and you get minus s by 2 dBz by dz at s equals 0. So, at Bs at s equals 0 was 0, but you slightly off from it, it depends on dBz by dz. Similarly, I can write the curl of B in cylindrical coordinates, and you will write the entire expression, and you will find that the only terms surviving are dBs by dz minus dBz by ds. All other terms go to 0. This is the phi component, and this is 0. This implies partial Bs by partial z is equal to partial Bz by partial s. Therefore, I can write from this partial Bz by partial s to be equal to partial Bs by partial z, which from the answer I have already calculated is going to be minus s by 2 d2 b z by dz square at s equals 0. And this tells you that Bz as a function of s is going to be equal to b z at s equal to 0 minus s square by 4 d2 bz by dz square at s equal to 0. So, that is one correction that we have gotten to Bz away from the axis. Now, I can use this to find Bs. So, we found that Bz at s is equal to Bz at s equals 0 minus s square by 4 d2 Bz over d z square at s equals 0. We had already seen on the previous slide that Bs at some s at z, obviously there is a z also, is equal to minus s by 2 dBz by dz at s equals 0. Now, I want to find the next order correction. For this, I again go to d bs, again go to the divergence equation, where we had written that 1 over s d by ds of s bs is equal to minus dB z by dz. Now that we have found bz to a certain s value, I can substitute that and write that 1 over s d by ds as s bs is equal to dBz by ds at s equals 0 minus s square by 4 d2bz over dz square at s equals 0, and there is one more d by dz on this. I will put a minus sign in front and plus sign here. Now, I have got a higher order correction, and this immediately gives you that Bs is equal to minus s by 2 dBz by ds, dBz by dz, sorry, this is dz, at s equals 0 plus s raised to 3 by 16 d cube bz by dz cube at s equals 0 plus higher order terms. So, we have gotten up to second order. What I like you to do beyond this is calculate the next order correction and specify what near the axis means. I would also like you to explicitly calculate corrections to magnetic fields component Bz and Bs for a current carrying loop in the xy plane. And third, once you have done that, related to that, plot the field lines near the axis. So, let me now conclude this lecture by saying that Biot-Savart law in terms of the current density is this: dV prime j r prime cross r minus r prime over r minus r prime cubed, and this tells you that divergence of B is 0 and curl of B is equal to mu naught j r, and then the equations above put a constraint on a variation of B, just like they did for electrostatic field, and then we solved a problem to calculate components of P when one component was known on the symmetry axis in a cylindrically symmetric problem. Thank you.